Hi, my name is Jessica Mao and I'm from the University of Texas at Austin. Today's video is part 2 of a 5-part series on factoring quadratic expressions. Today's video is on using manipulatives to factor quadratic expressions. Before we get started, let's talk about the foundation upon which this work is built. As you can see, there are 3 types of mathematical representations: concrete, pictorial, and abstract. According to Strickland's 2017 article, these 3 types of representations are not meant to be used in a specific sequence or hierarchy. In fact, they can be used interchangeably and flexibly. The goal essentially is to help students become proficient in using all 3 types of representations and to solve problems using any of these types of representation that makes the most sense to them. And this can help students with learning disabilities as well. Now let's turn to the document camera to see how we can use manipulatives to factor quadratic expressions. Before diving into problem solving, it's important to review what the manipulatives, specifically algebra tiles, actually represent. The bar represents the variable x, an unknown quantity, and the square represents x squared. And the cube stands for a unit integer or constant. A common misconception that students might have is assume the size of the pieces to indicate their value. For example, they might notice that 3 cubes are nearly the same length as an x bar and concludes that the bar must equal 3. This is incorrect. It's crucial to clarify with the students that the bar actually represents an unknown value and not a fixed value. So visual similarity does not determine the mathematical equivalency when we use algebra tiles. Once students have a solid understanding of what each block represents or what each tile represents, you can introduce a problem. Choose a problem in advance and begin by presenting students with a set of manipulatives that represent the product. Remind students that the corner piece, often an L shape, is meant to help guide the construction of a rectangle or square, which is the product in the center right here. When you give students these blocks, it could lead to exciting exploration in which students were to figure out how to fit all the manipulatives together like a puzzle. As students attempt to fit the blocks within the corner piece, they'll try various strategies. They'll probably make some mistakes, but that's okay because that's just part of the learning process. Ultimately, students should come up with a representation that looks something like this, as the product in the center of the centerpiece. If students are having a difficult time formulating this rectangle, you can support them by asking guiding questions. For example, remind them that what's inside a corner piece is the product, and that the 2 sides of the corner piece represent the factors. If students aren't sure where to place the blocks, you can ask them, what does this piece represent? Once they have built a rectangle representing the product, you're now ready to help them consider what the factors are going to be. You can remind students at this point that the factors should match the rectangle you created. The sides of the rectangle define the factors, and that the factors should align perfectly, and that no factor outside the frame should be longer or shorter than the side, or either of the sides. Okay. For example, you can think out loud for your students. If you have x squared in the corner, you know that it came from multiplying x by x, like so. Next, you might ask yourself, if you have 2 bars along the side, the length right here, and 3 bars along the width, what constant should be my factors? So if I have 2 x bars here, and I know that the other factor is an x, that means that this side of the factor must be 2, because 2 times x equals 2x. Likewise, we can say that we know there are 3 x bars, so if the constant is 3, and I know that the other factor of these 3 x's is x, it verifies that 3 times x equals 3x, like so. And finally, we can have the students check and say, okay, so I know that the factors, the constants for each factor is 3 and 2, and my last constant as a product is 6, and that is consistent. So one factor is x plus 2, and the other factor is x plus 3. And now students can check their work, asking themselves, does it make sense if I have 2 constants here and 3 constants here to have a total of 6 constants? And that 2 constants multiplied by x equals 2x, and that 3 constants multiplied by x equals 3x, and finally x multiplied by x is x squared. You can encourage students to take this learning further in 2 ways. First, you can have students also draw a pictorial representation of this by sketching the corner piece and where each block goes. Then you can also have students translate this representation into an abstract form or equation. So for example, if now that we know that the factors are x plus 2 and x plus 3, and they're multiplying, you can have students represent each of these blocks with the abstract form, in which this is x squared. And then we combine the like terms of x bars into, we have 1, 2, 3, 4, 5x plus 6 as our constant in the product. And your equation would be x plus 2 times x plus 3 equals x squared plus 5x plus 6. Engaging students with all 3 types of representation, the manipulatives, visual or pictorial, and abstract, deepens our understanding and encourage their flexibility in thinking. Students can then choose the approach that makes the most sense to them. This is just one way to introduce students to factoring quadratic expressions by giving them the product first and then guiding them to discover the factors. Be sure to provide practice problems that include both positive and negative integers to build their fluency and confidence in manipulating these concrete manipulatives, as well as representing them pictorially and in the abstract form. Thank you for watching this Dear Tailored. Stick around for the next video where we help students discover rules for factoring quadratic expressions.